This is Algebra 2, Unit 11, Lesson 9, and this is on infinite series. We've talked about sequences and we've talked about series, but we haven't talked about infinite series yet. And in this section, we're going to talk about series that go on forever, but in actuality, they do end up stopping at some point. And they are very specific situations when this happens. The formula for an infinite series is S sub infinity equals a sub 1 over 1 minus r, where r is your common ratio. And in order for an infinite series to exist, the absolute value of the r value has to be below 1 or less than 1. In other words, it has to be between -1 and 1. If it's a fraction that's higher than 1, it will not work. So it has to be something like 1/2 or 1/3, something like that. So you need to understand when we use infinite series formulas. And I'm going to explain that to you as we do the lesson part on the whiteboard. And the infinite series formula is S sub infinity equals a sub 1 over 1 minus r. A sub 1 is your first term, and then r would be your common ratio. And we have an infinite series when, well, first of all, it has to be geometric. And your r value has to be between -1 and 1. In other words, the absolute value of r has to be less than 1. So it can't be something like 3/2. That's 1.5, right? It has to be a fraction between 1 and -1. So like 1/2, 1/3, 3/4. Those would all be ratios that would work for an infinite series. So that's the first thing you need to know. If your r value is something greater than 1 or less than -1, then that infinite series goes on forever. It will never come to a stop, and so you're not going to have a sum, okay? And the difference between a series that is infinite and a series that we've covered so far is in the series that we've covered so far, remember, we've only added up specific terms. So we may have said go from the 1st to the 5th term, or the 100th to the 105th term. Add those terms together in a series. So now we're talking about series that eventually will come to a zero or a stop. And if you think about that, a real life situation of that, if there's a person on a swing and that person is pushed one time and they swing back and forth, well, eventually their swing is going to go back and forth a little by little and stop. So eventually that swinging motion will stop. And the idea of an infinite series is we could find the entire distance that swing moved or traveled if it comes to a stop, okay? But if it's a situation where something is continually pushed and it never stops, then that one's not an infinite series because it goes on forever. So it's kind of opposite of what you would think. An infinite series does come to a stop. And we call it infinite because we can figure out exactly how far that thing has moved. If it continues to move forever, then we can't get a sum for the motion of whatever it is that's happening. Another example of this would be if you have a ball and it drops to the ground and it goes up a certain percentage of the original fall or the last fall that it made, eventually, isn't that ball going to stop and just roll and come to a complete stop? So something that has a definite pattern, but then eventually will come to a stop, is infinite. It comes to a stop so we can figure out what that total distance it traveled is. So it is kind of confusing by name because in an infinite series, it stops. And normally when we think of infinite, we think of something that doesn't stop. Okay, so an infinite series is a series where we can specifically figure out a number that is associated with the total distance that series contains. All right, so if you think about that in terms of an example of a series where this happens. Well, if I start with 10, go to 5, then 5/2, then 5/4. If you think about that, r, we're still finding the r the same way. A term divided by its previous term will give us r. So 5/10 is 1/2. So r is 1/2. If I multiply 10 by 1/2, I get 5. 5 times 1/2 is 5/2. 5/2 times 1/2 is 5/4. And it goes on forever. And if you think about this, if we're multiplying by 1/2, isn't that fraction getting smaller and smaller and smaller until eventually that fraction is going to go to 0? It's going to be something so small that it has no length. So it's going to end. Okay? Again, this only happens when your r value has an absolute value less than 1. If I wanted to take this infinite series and find its sum, its final sum, well, I could say, okay, 10 plus 5 is 15, 15 plus 5/2, and then that plus 5/4, and that plus 5/16, or 5/8, that plus 5/16, and so on, and try to get an infinite number. I mean, I could try to do that, but we have a formula that works and gets the total answer very, very easily. So an infinite sequence, or an infinite series, is equal to a sub 1, the first term, over 1 minus r. So let's think about that. In this series, r was 1/2, a sub 1 is 10, so our infinite series is equal to a sub 1 over 1 minus r. Wouldn't we have 10 over 1 minus 1/2, which is the same thing as 10 over 1/2, or 20? Our final answer for that is 20. The infinite series has a sum of 20. So if this were a swing, and it went 10 feet on the first swing, then 5 feet on the second swing, and then 5/2 the third, 5/4 on the fourth, then eventually that swing will come to a stop after it has gone a total distance of 20, whatever that 20 might be, feet, inches, whatever it is. For this one, our r value, if I divide 3/8 by 1/2, we get 6/8, which is 3/4. So our r value is 3/4. So to determine if this is an infinite series, we would need this to be between -1 and 1, and it is. So this is an infinite series. I'm going to use the infinite series formula to find the sum of this series. And that's what your directions are here. Find the sum of the infinite series. So if I do that, a sub 1 is 1/2 over 1 minus r, which is 3/4. That would give me a 1/2 over 1/4, which is 2. So the sum of that infinite series is 2. For the next one, if you look at it and determine what your r value is, we divide any term by the previous term. So -12 divided by 4 is a -3. Well, this is a series. It keeps going forever. Our r value is -3. Now, what did we say about the r value? If it's an infinite series, if we can find the total distance traveled, then the infinite series has to have an r value where the absolute value of the r is less than 1. The absolute value of 3 is 3. That's greater than 1. This one is not an infinite series. It does not come to an end. It does not approach 0 as we move further toward the series. The numbers are getting bigger and bigger. In fact, they're going back and forth between positives and negatives. And you might try to argue that if you add them together, it's going to approach 0. That's not going to happen. So with this one, we would have to say that one has no sum, okay? I would prefer you say no sum if it's not infinite. We can't do that one because it doesn't match the criteria that we need it to. Here I've given you 3 series. Go ahead and copy these down, pause the video, see if you can find the sum of these, and then I'll come back and give you the answers in a few minutes. So here are your answers for these. In the first one, I divided 3/2 by 3, one term divided by its previous term, and I ended up with 1/2 for my r value. So my a sub 1 is 3. My a value, or my r value, is 1/2. So 1 minus 1/2 is 1/2. 3 divided by 1/2 is 6. So that one had a sum of 6. In the second one, my r value, -2 divided by 1 is -2. Negative 2 does not have an absolute value that is less than 1, so that one has no sum. For this one, if you look at this, 5 divided by 15 is 1/3. 1/3 is between negative 1 and 1, so we can do this one. A sub 1 is 15. 1 minus 1/3 is 2/3, and 15 divided by 2/3 is a 45/2 for our final sum. Another thing that an infinite series is very helpful with is understanding why repeating decimals can be written as fractions. You might recall back in Unit 1, we were talking about when or what number systems different numbers were a part of, and we said back then that a repeating decimal, it can always be written as a fraction, therefore it's always a rational number. And back then I told you that eventually we would get to where I could show you why that is the case. And that happens now with the infinite series. Here's why repeating decimals are rational. If you think about what you have when you have a repeating decimal, you've got 0.59, 59, 59, and that pattern continues forever. Well, we can write that as a series. We can say that that is 0.59 plus 0.0059 plus 0.00059, and we can continue that pattern forever. If you think about what you've got here, couldn't I add all those up to get my repeating decimal that I'm talking about? Well, if you think about that in terms of a series, now we know that if we take one term and divide it by its previous term, we can get our R value. What are we multiplying by to get to the next term? Well, if we divide 0.0059 by 0.59, we get 0.01. Now, 0.01 is 1 over 100. Now, if you think about that, is the absolute value of 0.01 less than 1? It is. So, this is an infinite series. So, we can do the formula S sub infinity equals A sub 1 here is 0.59 over 1 minus the R value 0.01. If we do that, we get 0.59 over 0.99, and if you simplify that fraction, isn't that just a matter of moving the decimal 2 places? S sub infinity would equal 59 over 99. That fraction doesn't simplify. This is the fraction that would be equal to 0.59 repeating. So using infinite series and its formula, we can convert any repeating decimal now to a fraction. So this fraction is 59 over 99. If we have a 0.8, think about what that means. That's 0.8 repeating. It keeps going forever. So if we add that or write that as a series, that would be 0.8 plus 0.08 plus 0.008 and then 0008, and that pattern continues forever. If we're looking for our R value, 0.08 divided by 0.8 is equal to 0.1. So my R value is 0.1, which is below 1. It's between 1 and negative 1. So my infinite series is A sub 1 over 1 minus R. A sub 1 is 0.8 and 1 minus 0.1. So we've got 0.8 over 0.9, which is 8/9. Now, how can we check these? Well, I could put 8/9 in my calculator as 8 divided by 9, and it does give me the 0.8 repeating. So you could try that if you wanted to. Now, here's something interesting that happens. I want you to do this one on your own and see what you get. This is something interesting that happens in math dealing with sequences and series. If you think about 0.9 repeating, and I ask you to convert that to its fraction, go ahead and use the same pattern with the infinite series. Go ahead and pause the video, work that through, and then we'll come back and talk about what's happening. Okay, so hopefully you've had time to work through this problem and see what's happening here. The 0.9 repeating is 0.999, and it goes on forever. And if I use the same principle dealing with the infinite series to do this problem and convert it to a fraction, look what happens. This is 0.9 plus 0.09 plus 0.009 plus 0.0009 plus, and it keeps going in that pattern forever. So this is an infinite series with our R value being 0.0, or with our R value being 0.1. I get that R value by dividing a number by its previous term. That gives us 0.1. 0.1 is between -1 and 1, so we're allowed to say that this is an infinite series. And if I plug it into the formula, I have a sub 1 over 1 minus r. Well, a sub 1 here is 0.9. 1 minus 0.1 is also 0.9. So look what happens. That gives us a 9 over 9, which isn't a fraction at all. That's 1. So if you ever hear somebody say that 0.9 repeating and 1 are the same thing, this is why. 0.9 repeating gets so close to 1, there is no real distinguishable way to say that they're different. And when we do the infinite series formula, it shows that. It proves that 0.9 is so close to 1, we're just going to call it 1. So that's just an interesting thing that might show up at some point. If you're ever asked to prove that 0.9 repeating and 1 are the same thing, there you go. It's infinite series. We're also going to have some word problems dealing with infinite series. So I'm going to go into the notebook now and do a few word problems with you, and we'll see how these are very similar. Okay, so now that you've got an introduction to what infinite series are, we're going to do a few word problems dealing with this. A ball is dropped from a height of 16 feet. Each time it drops, it rebounds 80% of the height which it has fallen. Find the total distance traveled in 15 bounces. So if you think about this situation in terms of a picture, if a ball is dropped from a distance of 16 feet and it bounces 80% of its original height in each bounce, and they want you to figure out how much of a distance has been traveled until that ball comes to a stop, and they give you that you're doing this for 15 bounces, then you need to figure out what your R value is first and what your A sub 1 value is, and then we can plug into the formula. So our formula is S sub infinity equals A sub 1 over 1 minus R. And in this, if it's rebounding 80% of its height, well, 80% as a decimal is 0.8. So that would be our R value, 0.8. And then if it is dropped from a height of 16 feet, then this height right here would be 16. So that means that our A sub 1 will be 16. So if we plug into the formula, S sub infinity will equal 16 over 1 minus 0.8. So if I solve that equation, A sub 1 is 16, 1 minus 0.8 is 0.2, and if I divide 16 by 0.2, I get 80 feet. So the total distance traveled by this bouncy ball is 80 feet. A child on a swing is given a big push. She travels 12 feet on the first back and forth swing, but only 5/6 as far on each successive back and forth swing. How far total distance does she travel before the swing stops? Well, in this one, our A sub 1 is 12 feet, and our R value is 5/6. So we're going to plug that into the formula. S sub infinity equals 12 over 1 minus 5/6. I am allowed to use this formula because R is between -1 and 1. Its absolute value is less than 1. So if I solve that, I'll have 12 over 1/6, and you can put that in Desmos to solve it, or you can do it in your head, whatever's easiest, and that gives you 72 feet as the answer. So most of these are going to have pretty simple answers. What you have to look out for is to make sure that the R value here is under 1, or it's between -1 and 1. Its absolute value is less than 1. In the next one, a ball is dropped from a table that is 24 inches high. The ball always rebounds 3/4 of the distance fallen. Approximate how far will the ball have traveled when it finally comes to rest. So our A sub 1 here is 24 inches, and our R value is 3/4. 3/4 is less than 1, so we're allowed to use the infinite summation formula. So S sub infinity equals A sub 1, which is 24, over 1 minus R, or 1 minus 3/4. That gives us 24 over 1/4, which is 96 And in this term, or in this problem, it would be 96 inches. A ball is thrown 12 meters in the air so that the initial up and down distance is 24 meters. A ball rebounds 95% of the distance it falls. What is the total vertical distance traveled by the ball before it stops bouncing? Go ahead and pause the video, see if you can get this one on your own, and then I'll come back and give you the answer. So I've plugged the information into the infinite series formula. S sub infinity equals 12, or A sub 1, over 1 minus 0.95. That would be the 95% as a decimal. So that's 12 over 0.05, which gives us 240 meters. So that's all you need to know for infinite series word problems. They're not too bad. Usually they're pretty straightforward. The main thing here is that you have to understand that your R value has to be between -1 and 1, or its absolute value has to be less than 1.